So today I want to tell you about two things that are related: Bernoulli numbers and Faulhaber's fabulous formula. So when I was a kid, I kept a journal, and I also had a math journal where I kept all my secret private musings about math. When I got to Princeton, I asked one of my professors, my first year in college, about a question that I was looking at in my journal, and she said, I don't know the answer to that, but you should go talk to this guy, John Conway. You might have heard of him. I actually only barely knew who he was at the time.
So you weren't like, oh my God, John Conway?
I had just had a vague idea. Yeah, which was probably good. So I went home and emailed him. And he said, come talk to me. I brought him my journal. He looked at some of the things I'd written in there, which was very kind of him. And then he told me about Faulhaber's fabulous formula and the Bernoulli numbers, and that actually led to what I work on in research today, and in an active area of mathematical research in number theory.
So you were introduced to these things by John Conway himself. Amazing.
Yes.
Do you remember the day?
I do, and in my regular journal, I journaled about it. It was in the spring of 1999. I'd have to look up the precise day, but it was a beautiful spring day in 1999.
Where do we start?
We're going to ask a few questions about sums of numbers. So what is the value of 1 to the k plus 2 to the k plus 3 to the k plus ... plus n to the k for k, some positive whole number? And just to make sure we're on the same page, so for example, if n equals 100 and k equals, say, 2, we're looking at 1 squared plus 2 squared plus 3 squared plus ... plus 100 squared, and so on. So if k is 0, this is really easy, because we've got 1 to the 0 plus 2 to the 0 plus 3 to the 0 plus ... It's just 1 plus 1 plus ... plus 1 n times, so we get n. If we look at first powers, then we have 1 plus 2 plus 3 plus ... plus n. And there's a formula for this, which people sometimes learn in school. You might know how to prove it. There's also a proof on Numberphile in some previous episode. And so this is often written as n times n plus 1 over 2. So we could compute this guy easily. Now, what if you want to work with squares or cubes? So what about this number from before? So we had these squares, plus n squared equals, or cubes, or fourth powers, and so on. So the question becomes, what are these numbers? How can we get it? And you can't just, if you try to just generalize the approach in that other Numberphile video from this guy, and you're like, okay, I understand that, so I've got good intuition, I'll try to do that for squares, you might be able to push things a little further, but once you get to cubes and beyond, that kind of trick is going to become just a mess. So, do we have more paper? So this is where Faulhaber's fabulous formula and the Bernoulli numbers come into play.
So is the fabulous formula what is going to solve that problem for us?
It is, yeah. Okay. Yeah, it's a formula that solves it.
All right.
Yeah, Faulhaber said, okay, if I want to look at 1 to the k minus 1 plus 2 to the k minus 1 plus 3 to the k minus 1 plus ... plus n to the k minus 1, that's equal to 1 over k times, I'm going to put something in quotes right now, and then I'll explain it because, well, there's two reasons it's going to be in quotes. So we're going to look at n plus b to the k, so we've gone down 1 here and up here, minus b to the k. And I haven't told you what this b is here. You know what n is, it's our whole number. These b's are going to tie into the Bernoulli numbers. This is going to be, I'll have to tell you what the stuff on the right-hand side is, but this is Faulhaber's fabulous formula.
I'm assuming Faulhaber themselves isn't the person who called it the fabulous formula.
No, and I'm not sure how it originated. Certainly John Conway called it that, but you would want to, I don't know whether it's safe to attribute to John Conway. He and Richard Guy in their book, do you know the Book of Numbers? They write about this in the Book of Numbers. Certainly sounds like a John Conwayism. So I'm going to have to tell you about these b to the k's. These b's are going to behave in a way that usually would be quite weird. Okay, so how to define b to the k. Now, first of all, I'm going to define a number b0. Look, we have a subscript here. This is 1. And I'm going to, that's a definition there. And I'm going to define b subscript k equals b superscript k. This looks terrible. It looks like I took a power or something and then I just used a superscript. I still have to tell you about this guy though. And then for k greater than 1, we're going to put b minus 1 to the k equals b to the k. This is a rule, and we're going to use this to define all the other b sub k's. So eventually things are going to drop down here.
Are b Bernoulli numbers?
The b sub k's, oh yeah, it says, and these are the Bernoulli numbers.
Okay, cool.
Yes.
Just checking.
Yes. This is the kth Bernoulli number.
Okay, cool.
Let's compute what b1 is, since all we know so far is the value of b0. So if we want to do that, we'll use this rule. We have b minus 1 squared equals b squared. So doing this, I get b squared minus 2b plus 1 equals 0, just skipping the step of canceling the b squareds. And so this tells me then b1 equals 1/2. And remember, we drop our subscript down, so this becomes the first Bernoulli number. So this is our first Bernoulli number. The value is 1/2. You can continue like this. You can keep computing these.
Right.
So if you, should I do another example?
Let's see the next one.
Okay, so now let's find b2. So for that, we have to raise now to the third power. And the b cubes are going to cancel again. And then I have minus 3b2 plus 3b1 minus 1 equals 0, having just canceled the b cubes already. And I know what b1 is because we just figured that out. That's 1/2. And so now I have negative 3, and I'll just drop my subscripts down since I know I can do that from our rule, equals 1 minus 3 times 1/2, since we just figured out that this guy is 1/2. So we have over here 1 minus 3/2 minus 1/2. Great. So b2 equals 1/6.
Okay, all
I'm
right.
not going to keep doing examples all day.
All right. So we get a whole bunch of Bernoulli numbers.
Yeah, we get a whole bunch of them. Yeah, so now we've computed a bunch of b's, and I assert, following what Faulhaber told us, I assert that we get this formula, so you can expand this out and plug in the b sub k's. I just want to say a little bit about where this comes from. So just to make sure we see what's going on in an example, we're going to do this with a small value of k. So if I want to know what 1 squared plus 2 squared plus ... plus, say we care about, and we just want to go up to 100 squared is, then what this formula says is, okay, our k here, this is k minus 1 here. On the left-hand side, we wanted the k minus 1, so that tells us k must be 3. So we have 1 over 3 here. And then we have our n is this guy, so that's 100 plus b cubed minus b cubed. And we're just in this little example going to expand what this looks like. 100 plus b cubed minus b cubed equals 3b squared times 100 plus 3b1 times 100 squared plus 100 cubed. And then I have a b cubed here that cancels this b cubed. So this is what we get. And then we say, I'm going to drop these guys down. So I have 3 times b2 times 100 plus 3b1 times 100 squared plus 100 cubed. And if you cared to compute this, you can plug these in because conveniently you just had me compute b1 and b2, so we could even plug these in here. Right. So now we've got 3 times 1/6 times 100 plus 3 times 1/2 times 100 squared plus 100 cubed, and you can compute this big number if you want. So now I'm going to just tell you a little bit about where this fabulous formula comes from. So let's look first at a slightly different expression, n plus b to the k minus, I'm going to subtract off n plus b minus 1 to the k. And when I do this, well, remember we had this rule here. So we had this thing. And so when I do this, I'm going to get this, using the binomial theorem, I'm going to get this polynomial. Looks almost the same on each side, except we have different powers of b and powers of b minus 1 there. And when I unfold this whole thing, I get j equals 0 to k choose j, n to the j. And then I end up with, over here, b to the k minus j minus b minus 1 to the k minus j. And if I look back, most of these terms are going to be 0 because I have b minus 1 to a power equals b to a power. And here I'm comparing b minus 1 to a power with b to a power, except for this rule only holds for k greater than 1. And so what we're going to be left with at the end when we work through this is k times n to the k minus 1. Okay, so we unfold this. We got a bunch of zeros except preceding the term n to the k minus 1. And there we are preceded by 1 times k. And so we were left with this. And so now when I want to get Faulhaber's fabulous formula, I have that, well, first of all, we've just seen that what this tells us is that n to the k minus 1 equals 1 over k times n plus b to the k minus n plus b minus 1 to the k. But I want a whole sum. I don't just want one term here. So what I do is now I'm going to, if I want to add up all the terms, so if I want to look at n to the k plus 1 plus n minus 1 to the k minus 1 plus dot, 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 all the way down to 2 to the k minus 1 plus 1 to the k minus 1, I'm going to have to add up 1 over k times, now I have n plus b to the k minus n plus b minus 1 to the k. That just takes care of the n to the k minus 1 term. Plus, I have n minus 1 plus b to the k minus, just to deal with the next term, n minus 1 plus b minus 1 to the k. And then I get to the next term, which is the n minus 2 term, which is going to go here, n minus 2 plus b to the k minus n minus 2 plus b minus 1 to the k plus dot, 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 until I get to the end where I look at the one piece, and that's going to give me a 1 plus b to the k minus 1 plus b minus 1 to the k. So this first piece is our n plus b to the k that we have at the beginning of Faulhaber's fabulous formula. 1 plus b minus 1, this is equal to b to the k. And everything in between is going to cancel because they have n plus b minus 1 or n minus 1 plus b. Addition commutes. So these cancel. Now I have n minus 2, and up here I have 2 times minus 1. So that's going to cancel, and so on. And we can keep playing this game until at the end, all we're left with is 1 over k times, at the end of the day, we get our n plus b to the k minus b to the k. And we get Faulhaber's fabulous formula. So I've skipped over a few details, but people who are interested can also check those. And that's Faulhaber's fabulous formula and the Bernoulli numbers. And one thing that's really cool with these Bernoulli numbers is they show up in lots of places. You might have seen them defined in other ways. They show up in Euler's formula for values of the Riemann zeta function at positive even integers. And those numbers there are also encoding really deep information from number theory, which is the field I work in. And so one of the reasons I really like these is they're not only convenient in solving this cute problem, is that they tie to really deep mathematical phenomena.
It was so nice not worrying anymore that I thought, I'm not going to worry anymore, ever again. I was going to study whatever I thought was interesting. and not worry whether this was serious enough, because you know you've got 1 2 at the end of it next time. Here you've got, maybe it's 2 2s, I don't know, but anyway it'll be 2s. So the left-hand sequence always ends in a 2, and the right-hand sequence, well look, it goes 1 1 1 3 1 2.